Welcome to Lesson 8, representing proportional relationships with equations. We are continuing in our study of topic B, unit rate and constant of proportionality. Okay, I'll start off just with a few points to remember here. You can see on your page you should have in front of you. Okay, some points to remember here. Proportional relationships have a constant ratio, or what we call a unit rate. Okay, constant ratio or unit rate. The constant ratio or unit rate can also be called the constant of proportionality. Okay, so all of those, constant ratio, unit rate, constant of proportionality, are synonymous. Okay. Now, what we want to ask, just to open up a discussion. Again, we can't discuss anything since you guys are there. I'm here, but you can discuss it with your parent-teacher, or just to think about it. How could we use what we know about this constant of proportionality to write an equation? And this is what we're trying to get to here, is this idea of equations, because algebra is all about equations. So moving a little bit closer to that. So if you want to, you could pause and discuss with your parent-teacher or someone else nearby how you might do this. Okay, so let's just talk about it a little bit. I'd like you to start thinking about this this model of proportional relationship by using an equation in this way. So if we know that the constant of proportionality k, we know that k, and we've done this in prior lessons, is equal to y over x. So we have this, okay, because remember when we had our chart or our table drawn, we know x, y, and then this column here, when we were doing finding out our unit rate or constant of proportionality, we knew it was y as a function of x, which is written y over x. Okay, so for in a proportional relationship, any given set of ordered pairs, and we call those ordered pairs, if you guys remember, harken back to when you've worked with graphs. Okay, an ordered pair is written like this: the x value and the y value. And all of these ordered pairs will come from a table. Let's just say, here we go, here's some data here, ordered pairs. So out of this here, we can write our first ordered pair would be 1, 2. Second one would be 2, 4. Okay, so these are ideas. These are what we call ordered pairs, and these ordered pairs come from some data source, which is usually a table. Okay, XY table. Okay, so if we know that this constant of proportionality here equals y divided by x, are there other ways that we could write this equation? Okay, could we rewrite this equation to solve for y, for example? Okay, so if we were to put y here, okay, and we knew the x value, we knew the unit rate, how could we solve for that? And again, we've seen this before, and we talked about this earlier. That would be be x times k. Okay, right? And how about if we wanted to solve for x? What would x equal? How would we get x? Okay, with x, we would know that x equals y times k. Okay. All right, because right here we have. So if we go to our table right here, we have 2 over 1, and then 4 over 2, which is our constant rate of 2, or constant of proportionality, or a unit rate. So if we went ahead and plugged these numbers in, we could take, for example, let's just take from this part of the table, we would know 4 equals 2 times 2, and that works. Okay, and if we did over here, 2 equals 4 divided by 2, that works. And if we looked here, we had 2 equals 4 times 2. Ooh, that doesn't work, does it? No. Okay. So in this case here, when we have solving for our x value, again, we are going to do x equals y divided by k. Okay? So right here. Oh, it says it 2. Hold on a second. I should just put, as far as an equation is concerned, that would be x. Okay? So different ways. We have 3 different ways to write equations. If we started from here, we also have this. This is not true, but this is true. So we could start plugging these equations, or start plugging numbers that we use in this lesson and beyond into these equations to figure out, actually to solve any problem. Now, when this does not work, when you have a graph that does not have this constant of proportionality, okay, or this unit rate that goes throughout the entire table, then these will not work, and that will be a test. In the future, in your future studies of algebra, you will come up to problems that have no solution. And that will be the case. There's no solution because there really is no unit rate or constant of proportionality. Okay. All right. So we're going to go ahead and go ahead now. We're going to look down here and next page, and let's do an example here. And this example is called, "Do we have enough gas to make it to the gas station?" Okay, now that's a really this is something I'm always looking at, and actually my vehicle right now that I drive primarily is electric, so I don't have to worry about gas. But my other vehicle that my wife drives, I do this, and I know I've calculated and I understand about how many miles per gallon that I get. There's my unit rate, and I could usually, by looking at how many miles I've driven, know how many miles I have left on in my tank. How many miles I have left to go. Okay, so let's go ahead. This is a real life situation here. So let's go ahead and read this. "Your mother has accelerated onto the interstate, beginning a long road trip, and you notice that the low fuel light is on, indicating that there is a half gallon left in the gas tank." Half gallon. Now, honestly, let me just stop right there real quickly. I don't think it's ever, that fuel light doesn't come on with half a gallon, okay? But these are just hypotheticals, but you usually have, I think I said, at least a gallon of gas when you get that light on there, or probably more actually. Well, anyway, that's just a little point there. But the nearest gas station is 26 miles away. So hopefully, when you're solving these problems, you're circling or highlighting the different numbers that you need to use in your calculations eventually. So your mother keeps a log where she records the mileage and the number of gallons purchased each time she fills up the tank. Kind of had a friend, actually, when I was in high school whose dad did this all the time. Had a huge, long list of the times he filled up, and always referred to it whenever he needed to fill up. So go ahead and use this. Here's Mom's log down here, her gas record. I want you to use this information in this table here, okay, in this table, to determine whether you will make it to the gas station before the gas runs out. Okay, you know that if you can determine the amount of gas that her car consumes in a particular number of miles, what we're trying to find out here is her miles per gallon. Also called that MPG if you've seen maybe car commercials on TV, or if you've ever gone shopping for a vehicle with your mom or dad. you'll see this mpg, or miles per gallon, and this is of course a unit rate. Okay, and that's what we're trying to figure out here. This is the unwritten column here, which we'll write in right now. So yeah, if you can determine the amount of gas that her car consumes in a particular number of miles, again miles per gallon, then you can determine whether or not you can make it to the next gas station. So I want you to look at this table and answer questions A and B, and actually I want you to just go ahead and look and see how much you can get done, A to E, and whatever you can do, do it. Pause right now and come back. Give yourself enough time to discuss this with your parent educator or someone nearby, and come on back and we'll look it over together. Okay, so let's take a look at the situation. The table here, I've just marked a few things. Just trying to remind you to always know that when we are creating a table, we're also looking at it as an XY table. So in this case, the number of gallons is your X value, miles driven is your Y, and then over here, this other column that I created, you might have created the same, is our K value, or our constant of proportionality, or our unit rate, which we express as miles per gallon, or mpg. Okay, so we went ahead and did this, divided across, and then the equation we're looking at when we create this table here is this equation here. It's K equals Y over X. Again, Y as a function of X. Y as a function of X here. So if we did that, and we would find out that we would have a constant of proportionality of 28 and 28 mpg. Okay. All right. If mom is doing very regular routes, maybe going to work and shopping or whatever, she may very well be very consistent. I know in my vehicle, highway miles and in-town miles can be different, sometimes drastically different. But if you're getting 28 miles per gallon in your gasoline-powered vehicle, you're doing pretty well, I think. Anyway, yeah, so our constant of proportionality, that's question A asks that, and it is indeed 28. K equals 28, and we've seen that right up here in our table. And what does it mean in this case? Again, they're always in this curriculum, we're always going to be asking this idea: what does it represent in this situation? Trying to keep everything in context. These are not just random numbers we're throwing out there. Sometimes they are, but anyway, but they do represent something. Okay, so in this case, we would say that we get 28 miles per gallon. Okay, or just to write it out in other words, the car travels 28 miles on 1 gallon of gas. Okay, so each gallon of gas is going to get us 28 miles. Okay, so this is what it means. All right. If we write an equation, and again you can see there's a little bit of a typo there, write and equation, but write an equation that will relate the miles driven to the number of gallons of gas. Okay, so it's going to be different now, where it's not going to look exactly the same. We're not going to have the K equals Y over X here, because we're trying to write an equation that relates the miles driven, and the miles driven is our Y, over here, okay, equals our constant of proportionality, our K, which is 28, times X. Okay, so an equation that relates the miles driven to the number of gallons of gas is this one: Y equals 28x. If we used other numbers or other variables, we could say M as in miles equals 28 G. which is gallons of gas. But for future applications, this one here, y equals 28x, would suffice. Would actually be much better. Okay. So now C asks us, question C, knowing that there is a half-gallon left in the gas tank when the light comes on, which again is not very realistic. Will she make it to the nearest gas station? Explain why or why not. And again, paying a lot of attention to this idea of explaining yourself. Okay. And the answer is no. Okay, hopefully you got that answer. No, she will not make it. And I don't know how she was, oh boy, how you have a half a gallon of gas when the light goes on. Just not really real. But anyway, in this case, she would not make it. Okay, because, why? Well, because we know that we go 28 miles, or Mom goes 28 miles on a gallon of gas. If she has half a gallon, we are going to, multiply 28 times 1 over 2, or 28 times 0.5. Okay, anyway, we want to represent our half a gallon, okay, equals 14. Okay, and we know that half of 28 is 14. Okay, so she can go 14 miles on that half gallon, but the gas station is 26 miles away. She is going to be 12 miles short of that gas station if that were the case. Okay. Yeah, and again, not realistic to have half a gallon in your tank. Okay, when the light goes on, but I mean, you could indeed have half a gallon in your tank at some point. So my advice to you when you do drive, I know you're a few years away from that, is to again log your miles if you can. Be very regular about that. Know your miles per gallon, and also don't ever let the light go on. Okay, just start calculating how many miles you have left at maybe a quarter of a tank, for example. Okay, so yeah, let's go ahead and move on to D. Okay, so in D asks us, using the equation found in part B, determine how far your mother can travel on 18 gallons of gas. Okay, solve the problem in 2 ways. Now, I'm not sure if this made any sense to you, but I mean, maybe it did. Hopefully it did. But the way they show it here, let's just take a look at that part B here. So we have our equation, y equals 28x, or m equals 28g. Okay, so let's go ahead. Y equals 28x, and just so we know, m equals 28g, so we know miles and gallons. Okay, so 18 gallons of gas, we're going to just plug that in, and if we did, I mean, we could just write this down arithmetically. We could just say, 28 times 18, okay, because we have our 18 gallons, and we have our 28. We know our 28 miles per gallon, okay? And then if we did that, we could, we know that equals 504. Now this idea of 18 gallons, I have to tell you that we're looking at probably a truck of some sort, a larger vehicle, car, maybe a large SUV. My vehicle has it's a smaller SUV. It's a Highlander. It says it's a 15-gallon tank. Always good to know how many gallons your tank is, because you can predict a little bit better. But this 18-gallon tank is pretty big tank on the vehicle. But that's a good boy. If you had that 18-gallon tank and you were getting 28 miles per gallon, 504. That's a good distance to be able to go on one tank of gas. Okay, especially when gas prices are on the rise. Okay. So this is more arithmetical, but if we looked at it more algebraically, we might say, so we start off with, again, m equals 28g. Okay, we plug in right here. We don't know miles, of course, that's what we're solving for, equals 28 times 18. And again, this is this idea of solving completely something in the future you need to get used to, writing your solutions out, and then m equals 504. Okay, all right. So more of a process here, but still we come up to that same answer, which is mother can go 504 miles if she had an 18-gallon tank. Okay. Okay, then E here says using the equation found in part B, same equation over here, determine how many gallons of gas would be needed to travel 750 miles. So again, now we're just plugging in numbers where we have them. So we have 750 miles given to us. We no longer have the gallon of gas. We just go ahead and use our equation, which is y equals 28x, and just reminding ourselves that the y and m are synonymous of miles. Okay, so that means 750 equals 28x. Okay, so this idea of 28x. So we don't know. X is what we're solving for right now. We're trying to solve for gallons of gas. So in this case, we would have to therefore go ahead and we can switch this around if we wanted to, but we could also algebraically, what we would do in this situation is that we would divide each side, okay, by 28. Okay, and again, we're going to talk about this more in the future. And actually, let me just do it this way with our division, because our division is actually a fraction, right? Let me just change the color here too, so we know we're doing something different. So we would go ahead and divide this side by 28. And again, this is something we're going to be doing a lot more in the future. Okay, because what we're trying to do is trying to isolate this x value here. We're trying to create this as being just one single x. Okay, so if we divide 28x divided by 28, we just get a very single and solitary x. Okay, and then on this side, what we're doing here is we're dividing 750 by 28, and if you went ahead and did that, you would get the answer 26.8. Okay, so 26.8. Okay, so 26.8 gallons of gas now would be needed to go 750 miles. And again, unless you have a truck with two tanks, you're not going to find any vehicle with any kind of just a passenger vehicle with a 26 or anywhere near a 26 gallon tank. Again, gas is heavy, so yeah, there are lots of different reasons for it. But anyway, yeah. So doing this algebraically, you can see we would try to again isolate this, isolate the x on the side as a single x, and do our division therefore. Okay, and maybe you did it a different way. Hopefully you are doing some experimenting with different equations right now. Again, equations are something we need to get very, very familiar with and very, very comfortable with. Okay, continuing to discuss this problem here with the miles driven and gallons of gas in mom's tank here. Wanted to do a little bit of a discussion looking at miles driven related to number of gallons of gas. Okay, so we have miles driven to gallons of gas. Okay, so gallons, put gallons there. Okay, and I wanted just to bring up these terms again. This idea of a dependent variable Okay, this is very, very important in science as well. We talk about dependent variables and independent variables. So I'd like to discuss that with you now. And just to ask this question, let's focus on the dependent variable first here. And I'll ask this question, and if you want to pause after I ask it, you can discuss this with your mom and dad or someone near you. So which part of this equation here, or this ratio here, which part depends on the other for its outcome? Which part depends? Is it miles driven depends on the gallons, or is it the gallons that depends on the miles driven? Which would you consider to be the dependent variable? Okay. All right, maybe pause, maybe not. But anyway, yeah, the number of miles driven depends on the number of gallons of gas. Okay, so we're going to have the miles driven. This is dependent. Okay, it is the dependent variable because based on the number of gallons there are in that tank, that's how many miles you can drive. Okay, so the dependent variable is going to be our miles driven. Okay, now independent variable, okay, is the other one. All right, now in terms of where they go on a graph, okay, on a coordinate graph, we remember maybe from the past that the dependent variable, this one here, is our y value. And see if I can get some graph paper up here. Okay, yeah, this is a graph paper. Okay, so again, if I this is quadrant 1, of course, we're working in. Okay, there's my y, there's my x. Okay, so again, my miles driven, this is going to be my dependent variable, is my y on the y-axis. This is going to be, if I was to create a graph, coordinate graph, miles driven. Okay, and so therefore the independent variable is the x, and it's the one that I can change. Okay, so if I put, in mom's case, if I put 10 gallons of gas in my tank, I know that I can go 280 miles, so 28 times 10. Okay, so it is the one that I can change. Okay, so and again down here, if I'm going to go ahead and always remember, you're always labeling. You're labeling your graphs when you create them. The graph is not complete unless it has labels, because it doesn't doesn't communicate exactly what it needs to communicate. Okay, so again, our y value is our dependent variable. Our x value is our independent variable. Okay, now just to reiterate again, our dependent values are going to be recorded here on our y-axis, okay, right here, and our independent values on our x-axis. If I just go ahead and take a table right here, now we're looking at an old beater car, maybe some old vehicle who big engine and a huge gas guzzler. This is not actually that unrealistic that a vehicle might get 5 miles per gallon. Okay, but if we went ahead and graph this right here, we would say 1 gallon here, 1, 2, 3, 4, 5. Okay, so you can see that we are putting our y values on the dependent values, which are the miles driven there, and then let's see, another 2 gallons here. Okay, so, and again, if we were to create this graph, we would find that is a really very, very messy graph because it's so darn steep. We would see that it does go through the origin, and it has a consistent line, all points on one line, which shows that it has a constant of proportionality. Okay. Now, in the future, what I want to stress to you too is that any variable may be used to represent the situation, any situation, as long as it is known that it is showing a proportional relationship in an equation. Okay, so when you multiply that constant of proportionality, or that k, when you multiply that by the independent variable, which is that x, okay, we're always going to get that y, okay? So you can plug in any value here. So, for example, in our situation, just flip this around so we have the y here. So y equals kx, okay? And in our case here, for mom's vehicle, we know that y equals 28x. Okay, we can plug in any value for x, and we can get y. We can plug in any value for y, and we can get x. Okay, so that's what this is so useful for. Again, in predicting, very, very useful in life. We think of math sometimes as we get further and further up in the difficulty scale of math. We see it as not being as useful, maybe practically, but all that we'll be talking about and doing this year, the 7th grade year, and your 8th grade year as well, very, very practical math, though it looks extremely abstract at times. Very, very practical, very, very useful, and just good for the mind. Okay, I'd like to give you a little time here to practice with this example 2, Andrea's portraits. Andrea is a street artist in New Orleans. She draws caricatures, cartoon-like portraits of tourists. I've had a few of these done in my lifetime, and hopefully you guys have too. Really, very talented people out there on the streets, these street artists. But people have their portrait drawn and then come back later to pick it up from her. The graph below shows the relationship between the number of portraits she draws and the amount of time in hours needed to draw the portraits. Okay, and you can see our dependent and independent variables written down there. They've actually given you here some variables, ways to refer to them. She has they have number of portraits drawn as the n, and time spent as t. Okay, so we'll go ahead and let you do numbers or letters A through C. Pause now and do that, and come back, and we'll just quickly check over your answers. We're kind of looking at it in a different way now. We're kind of taking, we're kind of decoding. We're actually looking at this. We're analyzing this graph now, and we are taking from there and creating ordered pairs. And if you want, make a table, coming up with equations just based on this graph. So using this graph here to actually answer several questions. Okay, so go ahead and do that, and come back. Okay, so in order to solve this this problem here, I went ahead and made a table. I'm not sure if you did the same, but hopefully you did. Just getting used to looking at how this table relates to the graph. Okay, so I went ahead and the easiest way to take out points is to actually find where we have places where our x value and our y value intersect perfectly, and you can see I put dots on those. I found three points where that happens. Okay, and those points were right here. This first one was 2, 3, and you can see that's in my table right here. My x value of 2, which is my time, and again it's on that independent axis right here, which is the x-axis, and then my 3 is the number of portraits, which is on my right here, my independent axis, the y-axis. Okay, Then the next point I had here was 4, 6. Okay, this is my coordinates here, coordinate pairs. Okay, and the next one was 6, 9. Okay, now what do each of these points mean? Okay, well, each of these points means that, for example, if I looked at 2, 3, for example, in 2 hours, Andrea can paint, or she can draw paint, I'm sorry, she can draw 3 portraits. Okay, if I look at point 4, 6, in 4 hours, she can paint 6 portraits, and in 9 hours, she can paint, 6 hours, I'm sorry, she can paint 9 portraits. Okay? So, therefore, if we went and found our K, our constant of proportionality, which we know is y over x, because we're always looking at this in terms of what is the y, looking at y as a function of x, right? Then we would go ahead and look at it this way. We'd have 3 over 2, we'd have 6 over 4, we'd have 9 over 6, and with our sharp eye towards proportionality and our knowledge of fractions, we know that both of these, 6 over 4 and 9 over 3, are both 3 reduced down to 3 over 2, so we have our constant of proportionality as 3 over 2. Okay. Now we are also asked to go ahead and look at, excuse me, going down here, let's go ahead and look at, so they want you to go ahead and write several equations that would relate now the number of portraits drawn to the time spent drawing the portraits. Now we can do that in a couple of ways. I mean, we could have t equals 3 over 2n. Okay, so, and again, let's look back to how we wrote this. Remember, our t was our x, and our n was was y. Okay, so if we change this here, we could have x equals 3 over 2y. Okay, we could write it that way. And we could, pretty much if we looked at it this way, we could also do, t equals 6 over 4n, but we don't really need to because we've reduced it down to this, okay? But if we looked at it this way, so if we go back for any value of x that we put in, we would multiply that by 3. So let me just go ahead here. So for any value of x, we would multiply that by our constant of proportionality, and we would get our y. So let's go ahead and let's do one that kind of makes sense. So if we had 6, our last one was 6 and 9. Let's just double it. So let's say our x was, come up with the coordinate point 12. We know our x coordinate, our x value was 12. What would our y value be? Okay, so let's go ahead and plug that in. And if we had our x, we know our x is 12 equals 3 over 2y. Okay, so in this case, we would have to, therefore, as we had talked about before, is go ahead and divide both sides. This gets a little bit complicated, probably not the best example to use on you right now, but if I did divide both by 3 over 2, and this is the easy part here, that is the y, okay? And so y, this one divides out into just plain simple 1y. But over here, if we divide 12 over 1 divided by 3 over 2, you know that it works out to actually be multiplied. It's their inverse operation. Okay, and so that would be 24 over 3, and hopefully you guys are following me here. But yeah, so our y value would be 8. Okay, so 12 and 8 would be the next point on our coordinate graph. I'm sorry if that seemed a little complicated. Maybe you can watch that a couple of times. I just need to assume that you do understand the idea of division of fractions and how you divide fractions. What I did is I took my 12 and I just turned it into 12 over 1, which makes it a bit easier to work with. And then when I divide by, so if I'm going to divide by 3 over 2, to make this easier here, what I do is I flip these and we do the inverse operation and we multiply. We'll talk probably in the future a little bit more about that. We're going to talk about fractions. And so what I would do there is do that, and then I go ahead and complete that, and you can see that right here. Okay, so again, watch this over a few times, and don't worry too much about it now. But just the idea is that the point I'm trying to make is that you can now always, when you know your constant of proportionality, you can always plug it in and get either your x or your y value if you have one or the other already. Okay, and again, that question C, keeping it all in perspective or all in context. So they want you to determine the constant of proportionality, which we have already done, which was 3 over 2. Okay, so explain what it means in this situation. So we know that the 3 part is the portraits, and we know that the two portion, or the denominator in this case, is the hours. So we can say that Andrea can draw 3 portraits in 2 hours. Now, very often we do things per a single unit, get that unit rate. So if we were to go ahead and create an equivalent ratio or fraction in 1 hour, she could paint 1.5 portraits. Okay, so kind of a not a very neat number. We don't write fractions like this usually, but writing it as a ratio, we would probably write. Excuse me here. Again, we like to use to keep it a little bit neater. We'd say 1.5 to 1, which is 1.5 portraits per hour. Is the same as 3 to 2. Again, this ratio here. Okay, these are the same. They are equivalent. Okay, so to close here, just go over our lesson summary, and then I'm going to have you go ahead and do your problem set, complete your exit ticket. Okay, and again, stay on track. So lesson summary: if a proportional relationship is described by the set of ordered pairs that satisfies the equation y equals kx, where k is a positive constant, again that constant of proportionality. Oh, okay, that's what they're saying here. Then k is called the constant of proportionality. I know, we are beating this really, really hard. Sorry, I just want you to get to know these terms, know them so well. They become second nature. So the constant of proportionality expresses the stress with the multiplicative relationship between each x value and its corresponding y value. Okay? That multiplicative relationship. So if you have your x value, you can multiply it by your k, or actually divide it by your k. Anyway, and get your corresponding y value. Okay, so this idea of there is a relationship, when we say multiplicative, we also mean division as well, because ratios are formed by both multiplication and division. Remember, not addition, not subtraction. Okay? Okay, so go ahead, finish up your problem set. Good luck, and see you in lesson 9.